Morning, everyone. Welcome to the mobile track. Next up, we have Stefan Esser with exploiting the iOS kernel.
Okay, welcome to my talk about exploiting the iOS kernel. And let me first introduce myself. I'm Stefan from Germany, and I'm mostly known for doing PHP security stuff. But since last year, I'm concentrating on iPhone stuff. I did the ASLR implementation for jailbroken iPhones in December. And then a part of the official jailbreak by the iPhone dev team in like April or so. And yeah, I partly work for a German web security company called Section 1, but I also work as independent contractor right now. So what I want to talk today about is a short introduction about iOS kernel exploitation, highlight some similarities and some differences to the macOS kernel. And then I will give a short introduction how to activate the kernel debugger in iOS. And then I walk you through the exploitation of a stack buffer overflow and the exploitation of a heap buffer overflow in the iOS kernel. I will not disclose any 0 days, so this will be bugs already public. And in the end, I will tell you something about the kernel patches used by jailbreakers to disable all these security features. So this is basically the things you are going after once you have achieved code execution in the kernel and you want to disable all the security. So let's start. When you look at the iOS kernel, you will realize that it's very similar to the macOS kernel, at least a large part of it, because the iOS kernel is based on the same XGNU source tree as macOS. At some point in time, they were like branched and sometimes branched back together, and so they are very similar. Well, the kernel drivers are a different thing, but just the main kernel, the core kernel, is more or less the same. When you look at the macOS kernel or iOS kernel, you will see that there are no mitigations against kernel vulnerabilities inside the kernel itself. So the kernel is only trying to protect as best as possible that the user space cannot do something with sandboxing and all this kind of stuff. But inside the kernel, there's no mitigation like stack cookies or heap canaries or something like that. This also means when you're looking for iOS kernel vulnerabilities, you can take the XGNU source code from the open source apple.com website and can just audit it. And you will find some bugs, some vulnerabilities, and yeah, or not. But you still can find something in there, and once you found it, you can exploit it. The other thing that's different is when you look at the bugs you're searching for, they're different between macOS and iOS because, well, I come to that now. When you look at macOS, you will see that userland dereference bugs are not possible because the userland and the kernel space are not sharing the same address space. In macOS, they are actually starting both at 0. And in iOS, it's different. In iOS, you have all the kernel above 2 GB, and the userland is below 2 GB. So sometimes these kind of bugs are exploitable, or you can use this feature during kernel exploitation. When you look at OS X, usually nothing is sandboxed. Nowadays in Lion you have several things sandboxed, but in the previous version there was nothing sandboxed. So the only thing you wanted to have on OS X was you wanted to get root. In iOS, that's just the starting point. What you need is you need code execution in the kernel to disable all the security features. And therefore, on OS X, code execution or memory corruption inside the kernel is nice to have, but it's not really required. You just need a bug that gives you root. In iOS, you always need memory corruption or code execution in the kernel because otherwise you cannot disable all the security features. And the last thing that's different is when you have a bug in a macOS, a kernel bug that is only exploitable as root user, you usually don't care because there's no code signing and things like that. So if you're already root, you don't care. And if you're already root, you're most probably also not in the sandbox and those kind of things. So you don't care about this in macOS. But in iOS, these things are very valuable because you require them to stay on the device when it reboots. You need to be able to exploit the kernel from the boot chain, and at that time you are root, so you can use bugs that are only exploitable as root. So the jailbreaking scene therefore distinguishes between normal kernel exploits and untethering kernel exploits. And with a normal kernel exploit, you try to get from the mobile user to the root user and break out of the sandbox, execute code in the kernel, and and the problem here is it must be done 100% in return-oriented programming. Because there's no such thing that you can just like upload code and call mprotect and make it executable. Well, in the newest iOS versions, there's like this dynamic code signing in Safari and so on. You might abuse that for that, but in the older version, it's not required. Yeah, untethering exploits, on the other hand, are already running as root, and they only patched the kernel to disable the security features, so you again need to have memory corruption or code execution in the kernel. And in the early days, you could just like use a short ROP payload and use a sysctl command to disable some of the kernel features, the protections, and then you can just upload a binary and execute that. Since iOS 4.3.0, that's not possible anymore. The untethering exploits must be done 100% in ROP. So when you want to get started exploiting, first you need a device. I recommend to get an iPod 4G because it's very similar to an iPhone 4. And you don't have this GSM and CDMA stuff, which will stop you from downgrading or make it harder to downgrade to older versions of the software. In addition to that, you still have a boot ROM exploit in it, so it's very nice to start with that. But of course, you can take your iPhone or something else, or your iPad, as long as you have like it in a way that you can actually work with it. So you should have it jailbroken already, so that it's easier to develop an exploit on it, or you should have a development phone. Just make it a development phone. But if you just try to use it a factory phone, you always have the problem that in order to do some analysis, you have no help whatsoever. You have to do everything blind. So, and when it comes to testing, you have two different ways. You can like crash the kernel and then look at the panic log and the panic dump and just analyze the values and do something. Or you can use a kernel debugger. Well, the kernel debugger is something Apple forgot or, well, left in the iOS kernel for no reason. Well, at least I don't know a reason, because there's no thing like users or iOS developers to create kernel drivers, so they don't need a kernel debugger. They're not supposed to do it. And but when you look at the kernel, you will see that it's still in there. You will find like the code, the KDP. You will find that it uses the boot argument for the kernel debug and things like that. So the kernel debugger is still in there. You can see it very easily. Actually, I'm not so sure if they will remove it from iOS 5 or so.
How do you debug the kernel otherwise?
Well, they can just like create a debug version for themselves and remove it for the factory phone. Of course you can do that.
Yes, you can do that, but what if they get a unit back from the field that's been panicking all the time? How do you introspect the kernel then?
Okay, yeah, when you want to do it like this, yeah, it's easier for them to do it. Well, they can still like try to do some, well, okay, at this time it's jailbroken, so it doesn't help you to have code signing on the kernel protocol, okay. Yeah, I would remove it, but I'm not having to support like millions of users. So, yeah. So anyway, they left it inside, they left the KDP inside. KDP is also the same thing as an OS X. The problem is KDP is designed to only speak Ethernet or serial. And when you have like an iPhone, you don't see like an Ethernet plugin or a serial plugin. And so you have the big question how to communicate with it. Actually, I don't know if this USB MUX-D protocol is able to speak UDP. I never tried that, so because I found another way. So the idea is actually very simple. When you look at an iPhone dock connector and see the pin out, you will see that there are two pins that are very interesting called serial RX and TX. And this is basically a serial, you can speak serial with the iPhone. And but the problem is there's no cable I know of that you can buy that will give you serial directly.
There is one now.
Yeah, okay.
Red Fire.
Great, you can buy it now for $50. I built it for $50. So the other question is if this gives you only serial or if it gives you serial and USB at the same time. Yeah, because just serial is sometimes very bad, so you want to have both at the same time. So this is basically, I bought these few ingredients. I will go through that very fast because you can look it up. It's not really hard. There are like a few ingredients and you just put them together. And I'm very bad at soldering stuff, so I was able to do that. I once nearly destroyed my Xbox with soldering, so yeah. So if I can do it, you can do it too. Yeah, basically what I did is I export both serial and USB because when you do you trigger the exploit, you do it usually by SSH. And having a wireless SSH at the same time while running the kernel debugger doesn't work well. So it's better to have it over USB, then it's more stable. You don't lose the SSH connection all the time. Yeah. So your next problem is that now you have like this cable and you can plug it in, but you don't know how to speak with it. So the nice thing is Apple ships a GDB in iOS, in the iOS SDK with ARM support and KDP support. Well, they could remove that at least. Yeah, but you can still use the old version then. However, it only speaks KDP over UDP and over serial is not supported by default. At least I don't know of it. But another guy had the same problem as me, but he was debugging MacBook Airs, I think. So he wrote a little proxy tool that will just speak fake UDP over serial. And yeah, you can download this. You have the slide on the CD. You just look up his name or the name of the thing, and you can download it. Yeah, and once you have that, you need to activate it. And like I said, you have to have a jailbroken iPhone for that, or an old device, so that you can give boot arguments. So with all the devices before iPad 2 key, you can just take redsn, the latest version of redsn, and it has a command line option to give arbitrary boot arguments meanwhile. So you can just put in debug equals 1 or something like that, and then you get, in this case, you get the debugger halting the kernel at boot time. Yeah, and once you have done that, you can just use GDB and connect to it with using the KDP functionality. Yeah, in this case, you attach to localhost because the proxy runs on localhost. Okay, so now you know how to use the kernel debugger. We will not think about it for the rest of the talk. So let's look into real exploitation. I want to start with a stack buffer overflow. And actually, I will start with the stack buffer overflow used for the untether of iOS 4.2.1 until 4.2.8, I think. Maybe I'm off one version. But the thing here is, this is one of the exploits that requires root permissions. But it's okay, because it's an untester, so it's somewhere in the boot chain. Well, when the userland starts up, I mean. And so you have root permissions at that time, so there's no problem. The exploit itself, or the bug, was found by pod2g, which is one of the chronic dev team. And what it is basically some functionality that, no, it's the support for the old HFS format. And when you load an HFS image and it's malicious, then it will trigger a stack-based buffer overflow inside a conversion routine that converts from Mac Roman to Unicode. Here's the function that does that. You will see the most ironic thing here is that there's a parameter to this function called max_charlen, which is unused. It's always a good idea to pass the maximum length and then don't use it. And what's even more funny is that the official fix for this vulnerability from Apple still doesn't check that. They just check it on few calls for this function, and they check before if it's overlong or not, but in some calls they don't check it. So there might be other ways to exploit this vulnerability still. So basically what it does is it takes the first character because it believes to be a Pascal string, and the first character is the length of the string. So it takes the first character and loops that often. So no size check. And it will just, when it's a character in the low ASCII segment, it will just write the character with additional 0 byte, like Unicode wise. And in the other way, it will look up the character in some lookup tables and write something. Well, we don't need that. We just ignore it. So how do you trigger this bug? What you need is you need a HFS image. And this is the header of an HFS image. It's actually inside an image at the third sector. And you can see there's one character array, which is, you can see it because there's the size is in red. And this is basically the name. Well, we can just ignore that. Just create a hex editor. You take a hex editor and create your image. So you see there's an image, a hex dump of an image. There's this marker BD, which is the marker for an HFS. There's some value set, and then there's just like a very long name. You see ABC and so on. This is like far longer than allowed. I think allowed is like 28 or so characters, or 20, something around 30 bytes. And but it's far longer. So and then you just load this. You can load it with code like this. And once you load it, you crash the kernel. So now, once you crash the kernel, what do? You go to this directory, library, logs, crash report or panics, and then there's a panic log. You look into it, and you will see something like this, which is quite complicated. But you only care at the moment about this, which gives you an overview of the actual fault, the register values at the time, and something like that. And you see you control some of the registers, like R4, R5, R6, and you can see where it crashed and where the function was called from, because you see the program counter PC and the link register LR, which is the previous function. Well, the return address to the previous function. When you look up the actual program counter you see here in IDA, you will see something like this. This is unexpected because you thought maybe you get total control directly, but it's not like this. So you have to trace it back and see why it's crashing there, where it's coming from. So you go to the function that's addressed by the link register. And you will end up in this function. This is a source code from XNew, so it's easier to see. So basically what happens here is the crash occurs inside the call to the function at the bottom, the UTF-8 encode string. And you can see that the overflow is supposed to happen in the other one, in the first function. So you see there's a way to skip out of the function between that by having unicount of 0. So, well, let's set this unicount just to 0 and try it again. So we look a little bit deeper with IDA and see into the stack layout. You see here the stack layout, you have the string, the UTF-8 len, the unicount, and a few registers, and the program counter. You see there's no stack cookie, so you can just like overwrite everything. And so we just improve our HFS image. And you see now we have set the unicount to 0 and try to set some values for our 4, 5, 6, 7 and PC. And then we try the same thing again and get another crash dump. And now you see you control all the registers R4 to R7, and you also control the program counter. One thing you see here is that you might expect that the program counter is 450045, but the lowest bit of the address of the program counter is actually used for switching between thumb mode and ARM mode. And in the control register, you can see that thumb mode is activated. So basically, you can subtract 1 from the PC, and you see it's like controlled. Well, I could like take a different example to make it more obvious, but I was lazy. I didn't realize that after I saw the crash dump that like this number was actually bad. So, okay, now you control the program counter. The next step is how you get code execution. Of course, you can jump anywhere in kernel space usually when you overwrite the program counter. And one thing about iOS kernel is that a lot of the memory, or maybe all inside the kernel, is somehow executable. I think Comex once said that this was different in earlier days. That's why he had some special kind of kernel patches in his old jailbreaks. But nowadays, there's no protection at all. You can just jump to some heap memory and it's executable somehow. I don't know if it's like broken or if Comex is wrong and it was never like this. It just works. Maybe it doesn't work in iOS 5 anymore. But I used it in my previous exploit for the jailbreak to just like have some heap memory that I'm just jumping into it. Yeah, and the other problem is you need to know the address of the code you put in there. And when you're into macOS exploitation, you know that there's a lot of papers or so from Nemo, and he also wrote a chapter of the kernel exploitation book about OS X exploitation. And he shows you some ways to get like stuff into the kernel at a fixed address. Not fixed address, but an address that you can leak easily. I don't know if this still works because I don't use that on iOS, but it should still work. I think I tried it in the past and it worked, so maybe it still works. Okay, what can you do else? The next thing is we can like return into the kernel itself and use kernel level return oriented programming. And because there is no RVX protection, or no NX protection inside the kernel, your ROP payload is very short. You just like jump to copy some memory from user space into kernel space, and then you just return into that copied memory. Of course, it only works if you know the address in user space. But usually when you have like a kernel exploit, you can map memory somewhere, and yeah. Yeah, and it's very attractive to have return-oriented programming in the kernel because there are not so many different iOS kernels around. And when you use the gadgets only in the core part of the kernel, they're even the same for multiple kernels. If you use something in the driver, in the space of the drivers, they are not the same because the drivers are like shuffled for devices, for different devices. But the core kernel is always like the similar or same for the same CPU. And firmware version, naturally. Yeah, you can return to it and then you have the execution. The problem here is in our demo bug, we cannot do that because it's a Unicode overflow or Unicode conversion overflow. And the conversion routine doesn't allow us to write addresses in the kernel space, in the kernel code space. So we cannot just return there. So we need something else. I also thought about like a partial address override, which would be possible here, but you would still be very limited, and it's very unlikely that you can do something with it. But luckily, this is iOS and not macOS. So I told you in the beginning, the user space here is mapped into the same address room. And therefore, you can just return to an address in user space. For example, you have like a binary that maps executable code at this 10000 or 10001 address, and then you just return there, and it executes your code. The only problem here is it must be marked as executable, the memory. And one other thing is, when you look at the exploits of comics, he always does an ALLOC of this address. The other jailbreakers don't do that. I guess Comex does that because he wants to protect against some mapping out of the memory. I always also do that because Comex does it, and usually what he does is quite useful. So, but you see, when you look at the exploit of like the chronic dev team, you see that it's not really needed. It's usually still works. It's yeah. Well, the idea is that you like hardwire it so that the kernel doesn't like remove it while you jump into the kernel. Yeah, and you just return there, and then you have code execution. So it's very simple. You just map your payload at some point executable by loading a mach-o library, and then it's working like that. Okay, so stack overflows are very simple. Let's get to heap buffer overflows, stack buffer overflows, sorry, not to insult someone here. So it's stack buffer overflow, not stack overflow. Yeah, and yeah, let's go to heap buffer overflows. And this time I show you a bug of mine. It's quite complicated to exploit it. It's inside the socket option handler for the ndref protocol of this ndref set DMX spec opcode or whatever you call it. And basically there's a dmux count, and you can set it to a very high value, and then you trigger an integer overflow in a multiplication for memory allocation. And again, it requires root permissions, and nowadays it's closed by Apple. Okay, so the whole thing is a little bit complicated, so I will walk through this a little bit different than the Stack Overflow. So you see, there's a dmux count, and you see there are some memory allocations with some macro called malloc, and you see every time it uses the malloc, it does a multiplication inside, and there's like no check that there's like a small dmux count, so this cannot overflow. So in both cases, it can overflow, and in the end, you see a copy in, and you might think that this is like the overflow here, but it's the buffer overflow here, but it's not the buffer overflow because the size you're copying is also calculated by multiplication, and so of course this is the same small number that you get in the allocation, so there's no overflow. Yeah, for the buffer overflow, you have to go to the end of the function. In the end of the function, you see that it loops through all the input and converts it into a different format. And you also see there's an error condition that you can trigger in order that the loop breaks, so you don't like copy until the end of the memory so that you crash. So two things you want to know is what can you write and can you break out of it? So you look into this function. And you will see that it's quite easy to skip out of this function because there are two conditions that will exit the function immediately. So it's very easy. If you don't want it to crash, just put this kind of values there, and it will not crash because it will stop the loop. The other thing that's less nice is you see that you don't have much control over what you're actually writing. Yeah, you control the type, yeah, but it's only like 2 bytes, and there's some limit on it because of the check before. And okay, there's a length field that you write. It's also not very nice. But the other thing that's written is very nice. And in this case, it helps you to exploit it because it writes a pointer to data you just wrote into the kernel. This is very nice because of how you exploit the memory manager. But we come to that now. Well, yeah. If you want to trigger that, This would be the code. The problem is when you execute this code, it will not crash because the actual checks are so good that these two checks in the beginning of this function, they will most likely stop the execution in the very first loop. So in the very first loop of the overflow, so they will just drop out and there will be no overflow. So in order to actually cause an overflow, you have to call this socket option once with a normal dmax count so that you can fill a block of memory with whatever data you want. And then you call it again with the overflow, and it will reuse the same block of memory if you did the heap manipulation correctly before. And then you, at the point where the overflow is, because you're in the same block as before, you can just like overwrite with the data that was put by you before. But you don't need to know the details. The exact walkthrough to every line of the exploit and the source code for the exploit will be released somewhere later in August. So you saw that it's using some memory allocation here in malloc. With a macro called malloc. Malloc is a macro that calls a function called _malloc. And this is just a wrapper around calloc. And the thing, what it wraps is it adds a small header to it, which contains a size field. And it needs the size field to later free the right thing. And calloc itself is again a wrapper around two different allocators, the kmem allocator and the zone allocator, zalloc. And one of them is used for large blocks, and the other one is used for small blocks. We are only interested in the small blocks right now, so we don't care about the other one. So zalloc is a zone allocator, which means the memory is divided into zones. Well, let's call it divided into. And you see there's a quite long structure that defines a zone. And this structure has the possibility to have a lot of flags for the zones, but we don't care about this right now. And each zone has a name, like buffers or files or something like that. And the other thing about zones is that each element you allocate in a zone is of the same size. So when a zone is created, you say every element in here is like 128 bytes. And the other thing is when you have a free something in the zone, it's put to a zone, a free list that is started with a pointer inside the structure. What you don't have, if you don't have the debugging kernel, you have no way to know all the memory pages that belong to a zone, unless you are somehow able to free all the memory and then go through the free list. But if there's like a page belonging to a zone that is full of allocated blocks, there's no way to know that, because there's no pointer back if you don't have like a debugging kernel. So when you want to know what kind of zones there exist, just on OS X, you can just like use the setprint utility, and it will dump something like that. And you see there's a lot of calloc zones with a number attached. And this is basically for the calloc allocator. It uses a lot of different zones, always powers of 2 for the size. And so when you request something with kalloc, it will check what size, how much bytes it needs to the next power of 2, and then it will use this kind of size for the allocation. Okay, let's look at a new memory page, a new zone. When you have a new zone that's completely empty, there's no free list, there's no memory, nothing. And the first thing that happens is it will allocate a memory page. And like I said, there's no like pointer back. So the next thing that happens is we'll divide the zone into elements. Let's say 128 bytes. And then each element is added to the free list. And you see in the end you have like the free list in the reverse order. And then once you have this zone ready to be used, You can like allocate memory. It will be removed from the free list. Allocate again and again and again. And you see only the free elements are in the free list. And once you start freeing the elements again, in this case you freed the 5th element, then you see it's put back on the free list. It's like a normal, well, a simple free list. Yeah, let's do this for the other elements. So now you see you have still the same elements in the free list, but there's a different order. Internally, this is implemented as a single linked list with a zone struct pointing to the head of the list. And the free list, the pointer for the next element in the free list is stored inbound. The first 4 bytes of a free block are used to store the pointer to the next element in the free list. And Apple uses some macros for that, which look very complicated, but you don't care about the gray stuff. Just look for the green stuff for a moment. What it does, it's in this case, you remove something from the zone. That means you allocate the memory. So what it does, it looks up the current head of the free list, takes this, returns that. But before it returns that, it takes the pointer to the next element in the free list from there and makes this the new head. So there's a lot of debugging code in there and sanity checks and things that would make exploitation harder, but they are disabled by default. You need to set a special debugging boot argument to the kernel to actually activate it. But I saw in the Lion source code that Apple, obviously for a while, they introduced this new boot arguments, and they obviously tried to activate this by default. They disabled it again, but it seems they might consider to activate this in the future. I don't know, there were some bug numbers attached to it, so they disabled it again. I don't know why they disabled it again, but maybe in the future they will just enable it for all things. Similar, when you actually free something, it's the reverse thing. You just go to the head of the free. No. When you free a block, you take the momentary head of the free list, write it into the first 4 bytes, and then you set the new head to this free block. And again, there are some sanity checks which are disabled by default. Okay, how can you exploit that? Of course, when you have a heap overflow, you can always attack the application data. What you try is you carefully allocate and deallocate so that you control the heap layout. And what you want to have is like a buffer with a very interesting kernel structure behind a buffer that you overflow. And the impact depends on actually what you can write and what kind of structures you overwrite. At the moment, we can just ignore that because there's no mitigation inside the kernel heap at the moment, so it's easier to use the other way, especially for the exploit we are doing. So we remember that for the future, right now, we just exploit the free list of the zone allocator. So what we do here is we just like allocate and deallocate again and control the heap so that we have a free block behind our overflowing block. And when we overflow the block, we control the first 4 byte of the free block, which means we overwrite the next element in the free list. And so now when memory is allocated and this element that we have there, the free block, is allocated, then the pointer from there is taken and put on the top of the free list. So afterwards, the next element that is allocated will be actually the pointer we gave it. And when this is returned and filled with application data, we can write nearly everything everywhere. So how do you do all this kernel manipulation thing? You usually need heap manipulation primitives, like things that allows you to allocate a block of memory in a specific size and to deallocate some memory. And in our case, it's very easy to do that because we are dealing with NDrive sockets and anyway, so we can just take the NDrive socket again. And when you connect an NDrive socket, you can give it a name. with like a small but arbitrary length. And if you do that, you control the size of the block that is allocated in heap. So you just use different lengths for the socket name, and you can allocate different kinds of memory. And again, when you want to deallocate the memory, you just close the socket. So you can allocate and deallocate. And yet now you do something called heap Feng Shui. I guess most people know that. It's a term created by Alex Sotirov. And yeah, it basically describes the whole thing, like how to get a heap into a control state from an unknown previous state. So what you do normally is, you can see that the orange boxes are actually allocated memory, and the gray boxes are holes in the memory. What you do first is, you allocate memory of this block size as often as there is a hole. And afterwards, you allocate some more, that you have a bunch of consecutive memory blocks. And now you can poke a hole by closing one of the sockets, and you poke the hole there, and then you do it again, so that you have a second empty block. And when you allocate something now, the last free block was the top of the free list, so the last free block was this one, so when it's allocated it gives you this. And if this overflows now, you overflow the free block, and you can do this thing like replace the next element in the free list. So this is the normal way how you do like a kernel, like you do heap Feng Shui. So because normally you have no idea about the state of the kernel, of this kernel heap, and so you usually don't know how many holes there are in the memory. So you don't know how often you have to repeat this allocation until you have like really consecutive memory blocks. But Apple is very nice here. I showed you the zprint command line tool, and actually it's the same technique. It's used a kernel function called host zone info, and this function gives you all this information you saw previously in the zprint utility. It gives it to you in a form of a structure, a C structure, and this contains the count of elements actually allocated at the moment in the zone. It gives you the size of the zone at the moment, and you can divide that by the size of an element, and you know how many elements should be allocated. And when you know how many are allocated and how big the zone at the moment is, then you know how many are free. So you know exactly how many holes there are in the heap. And this gives you the idea how many allocations you have to do to fill all the holes. So you know exactly in iOS and macOS, you know exactly when the kernel heap, when all the holes are closed. Well, of course, they could remove the function, because I don't know if they really need it. The point is, even if they remove it, then, well, then you do it the old school, and you just repeat as often as you believe it's enough. So you repeat it a few thousand times, and maybe a little bit more, and yeah, at some point you will be out of heap holes. Well, the other thing is, because you can request this information, you know exactly when a new block, a new page is added to the zone, and then it's easier for you to know exactly where two memory blocks are relative to each other, because then you know exactly that this memory block is right in front of the other, because of the reverse order. Otherwise, you might end up in a situation when you have like one memory block in one page and one memory block in the other page, and because of the reverse order of the free list, you don't know which one is before the other. Okay, so to make things short, in order to do to get code execution here, you have, well, we attempt to overwrite a free block, and the idea is to replace the pointer inside the free list. But we cannot do that because we cannot control what is overwritten by overflow. We only know our overflow is writing a pointer, and it's writing a pointer to data we control. So, okay, we let the overflow do that. So the overflow will write into the free list pointer a pointer to our data. It will do that for us. So the next time something is allocated, it will actually put our block that we control into the head of the free list. The next time something is allocated, the block that we completely control is taken and returned, and the first 4 bytes that we completely control will be made the head of the free list. And then again, you take the next allocation, and now the pointer we provided will be used. This means we can put it anywhere in memory. And a nice place is in the middle of the syscall table. So the next allocation now will return the middle of the syscall table. And if the kernel copies some data into this just allocated block, we can write in the middle of the syscall table. And what I did in the exploit was I was using some area of the syscall table that's filled with unused syscalls, and I just used one so that the system wouldn't be interrupted. And in this case, it was 207. The stuff around 207 is there are a bunch of unused syscall, so this was the easiest way to do it. So I just write in the middle of that, overwrite the syscall handler for 207, and then I just have a user space code that calls syscall 207, and voila, I'm in the kernel. And of course, I can do all these kind of things again to like return to userland code, or what I did was I was returning into the syscall arguments. So I made it a syscall with a lot of arguments, and then I returned into a kernel address that would, BLX jump into the register 1, I think was it, into register 1, and register 1 was a pointer to the kernel arguments, so I jumped into my own kernel arguments, and like I said, it's somewhere on the heap, on the kernel heap, and it's just executable. So yeah, that's what I did. In the latest exploit of Comex in jailbreakme.com, he did a far more complicated kernel rob payload, but it's not always needed. Okay, let's get to the last part of the talk, the jailbreakers kernel patches. First thing is, what do the jailbreaks actually patch? It depends on the jailbreak, on who wrote it, and what bug they exploit, because especially when you have a heap overflow, you sometimes have to repair some stuff. I was a little bit lazy. I just removed the free of the destructed heap. So I just removed the free comment, and so the corrupted memory was just not freed. It was kept alive. And well, it didn't cause any problems I know of. Well, you waste a lot of, not a lot, you waste a bit of memory with that, but well, it worked. And if you want to do it cleanly, you have to go through the free list and figure out what page belonged to which of the zones, and then put each element back in the right free list and things like that. So it's a little bit tricky. Okay, but the other patches inside the jailbreaks are just disabling security features. And they're also different because the different groups patch different places. And nowadays, most of them rely on patches developed by Comex because they seem to be the most stable. Okay, sometimes he has a patch that doesn't work at all, but yeah, well, you just tell him and he will find a better one. And it's always easier to ship out the complicated work to other people. No, don't invent the wheel twice. So he does it all the time, so you just take it, and he has you can see it on GitHub. You can download it and see what he's actually doing and how he finds those places to patch. And I would just go through all the patches he's doing just to give you an idea what he's actually doing. I'm actually quite fast. Okay, so the first thing it tries to disable is the code signing. And therefore, it's process restrictions and code signing. And the first thing it does, it disables a sysctl variable called proc_enforce. This is the same variable that's previously used. Previously, ROP payloads were just like disabling it as root user, but with 4.3.0, Apple decided that it would be better to have this as read-only variable. So with 4.3.0, it's not possible to set this as root anymore. So you have to patch it from the kernel. And this actually allows you to execute wrongly signed binaries. The other thing it disables is, or enables better, it enables the CS enforcement disable flag, which is the boot argument to the kernel, and this disables the enforcement of code signing. This allows you to get around the code signing stuff. The next thing that's done is there's a function inside the kernel that is called pe_icanHasDebugger. And in earlier jailbreaks, Comex was just replacing that with the return 1. This turned out to be bad, because that's the reason why Comex is not the one who did the kernel debugger first. Because when you just return 1, the kernel debugger will not work. Well, no, that's not true. It will work, but the halt on boot feature will not work of the kernel debugger. It will then crash. So nowadays, Comex just looks up the, you see in the second line of the function, it's requesting a variable from memory. And nowadays, Comex patches this variable to 1. So then this function will return 1 and everything is okay. And according to Comex, what it does is it will allow that the Apple mobile file integrity driver will allow non-signed binaries. Previous was for wrongly signed binaries. This is for not signed binaries. It also disables various other checks. And like I said, you need it for the kernel debugger to run perfectly. Yeah, so that's what you need to know about this. And it's just setting 1 byte in memory to 1, so it's a very simple patch. Then, especially in the older kernels, there was no way to have read-write executable memory. It was simply forbidden by the kernel to have something like that. In the newer kernel, you have this dynamic code signing, so there are exceptions, as far as I know. Yeah. You're commenting all the time. Yeah, so basically, the patch from Comex replaces the check with a knob. And so now memory can be read-write executable. Otherwise, if that's not patched, then the kernel will see, oh, there's a prod execute, and it will just clear it. This just allows you to have the memory at all, the read-write executable memory. There's a second patch required to allow mprotect to have read-write executable memory. So here there's a similar check, and for some reason, well, Comex choose a different way to patch it. Here he just patches the bit clear opcode directly and just clears no bit. Previously it replaced, yeah, previously it was a 4th bit and now it's the 0th bit that he clears, which is not used in this case. Yeah. I think that was it, or yeah. Well, anyway, he writes a 0 there, and so that this opcode will not do anything that's affecting the code, the RWX memory. Yeah, the next thing it's patched, and if you see the slides from the CD, you will miss this slide because I had like a few slides missing when I submitted it to Black Hat. So the next thing that was patched is the AMFI binary trust cache, which is like a cache for all the trusted applications. And comics just replaced it with a return 1 so that it's not used. And the next thing is, when you look at the jailbreaks, actually when you look at the test-read jailbreak that is fresh for a new iOS version, so you use Red Snow on a new version it was not designed for, then you will see that some applications won't work. Like when you try to start Safari, it will just crash. This is because it doesn't patch the Sandbox in the plain Red Snow version for something that it doesn't know. And the reason here is when you jailbreak, it moves all the stuff around. All the applications are moved around. And of course, the sandboxes are not working anymore because now when it tries to extract something, it's not in the original sandbox policy and it will be like killed in this case. Oh, actually, I should show the slide. So what Comics does is he goes to the function called SB evaluate, sandbox evaluate, and puts a hook in there. And the hook basically redirects it to some code that you can also look at GitHub. And this hook will replace the logic of the SB evaluate function to check for specific paths. So if the access is outside of private var mobile, it will be allowed. If the access is inside private var mobile library preferences apple something, it's going through the original evaluation. It's like passing to the origin handler. When it's in another subdirectory of this private mobile library preferences, then its access is granted. And everything else goes through the original check. So you see that the sandbox is not completely disabled here. They just made some exceptions so that it would still work. Yeah, and that is like the presentation. There will be a bunch of downloads that I will upload to my site once I'm back in Germany and repaired the server, which is broken at the moment. Yeah, it's stupid when like server dies when you're not in the country. So I will finally release the IDA scripts that I used in the presentation from Singapore. I will release a jailbreak configuration tool that allows you to configure the jailbreak to disable only a few of the protections. This was requested by Charlie Miller because it makes exploiting on a jailbroken device more realistic. I will upload the latest slides because these slides are a little bit different from the one that I submitted to Black Hat. I will also update the white paper. And some other things I will upload, like a description of the exploit, the source code of the untether, and things like that. And you can get it at antidote.com. And the server is broken at the moment. If you want the slides before, just drop me an email. I can send it to you. And any questions? Oh, before I forget, please fill out the feedback forms. Otherwise, any question?
How long did it take you to go from draft to export?
What?
How long did it take for you to go from your original draft to your export?
For the second bug. Well, the problem is it took a very long time because of one simple thing. At the time when I found the bug and did the exploit, It was, well, it took a while to do the original exploit, but then suddenly 4.3.0 came out, and I could throw the exploit into the trash can because suddenly the whole exploit had to be completely ROP. So it took a while to build a ROP framework and then port all this kind of things. So yeah, like maybe a week or so just in my free time and something like that, yeah. More questions? No questions? Okay, then I'm... Sorry, there's one last thing. I told you I will release the jailbreak configurator, and this will look something like this. So a simple application that allows you to switch off and on these things, which is like 10 minutes of, well, the GUI is 10 minutes of code in Xcode, so it's not very hard. Just communicating with the jailbreak is hard, and I'm also trying to speak with Comex to like make this usable with jailbreakme.com. Yeah, that was it.